Okay, welcome back. This is our last lecture for this class. And as usual, I'm going to give you something kind of strange to leave you with. We're going to talk a little bit about lasers tonight, but in the context of what we were looking at the last couple of lectures, which is Huygen's principle and a kind of a stranger application to it. As just to remind you, there'll be no class on Monday, and then there's a test on the homework on Wednesday night. And then on a week from Monday, is our final exam. Okay, and I'll try to make all that official with an announcement for all that stuff tomorrow off of e-learning, so you should get an email on that. Any questions on those logistics? Did I miss anything? Have I forgotten some public service announcement, or anyone think of any issues or worries? Oh, I know. On the homework test, it's closed notes, no book, no calculator. On the final, you're allowed 1 page of notes, and you should turn it in. 1 8.5 sheet of 11 by a page of notes, and turn it in. Okay, with the test. Okay. All right. Now. So I want to talk tonight about an application to the Huygens principle that we looked at last time. And if you remember, the key part of the Huygens principle was the spherical wavefront here, right? And so what you do is like all of our convolution approaches, you take a field and you integrate it or convolve it over an aperture with the spherical wavefronts. And what you're doing is you're basically taking that aperture and smearing it with a large number of spherical wavefronts. In this particular case, you'll notice the subscript u p minus 1 calculates a u of p. And so what this is about is I thought I got rid of this guy. Ugh. I got to learn how to use this monitor better. There must be an easier way to clear all that off. So what we're doing on this with this integral is, in this particular case, is we have an aperture here, and then we have another aperture here, and then we have another aperture here, and so we're propagating from p minus 1 to the p aperture to the p plus 1 aperture. And so what we'll do is we'll line this guy with spherical wavefronts. We'll propagate them. They'll diffract out. So they'll overfill this aperture here. And within the aperture, part of that light will scoot through the aperture and propagate out again. Okay? And so what we'll do is we'll take the second aperture and we'll line it with spherical wavefronts, but we'll weight them so that they'll have more amplitude in the center than at the edges, just because of this diffraction from one to the other to the other. Okay? And if we continue to do that, you'll notice that a strange kind of filtering happens. The high frequency, and I mean not time frequency, but the high spatial frequency components, the really sharp wiggles, will diffract much faster than the slower distributions, the slow variations. And so these set of apertures, again and again and again, will spatially filter the electromagnetic radiation. And so it'll act. The succession of these filters will act as a spatial filter, a low-pass spatial filter, a smoothing function. Okay? And that's a very interesting opportunity, because any time you can do some filtering means you can do some sorting of information, and so that's kind of a nice thing to be doing. So this integral here propagates a disturbance to the next aperture, and then we would feed that back into this and do it again and iterate again and again and again and again. And it's important to remember that this is a complex quantity. This piece is a complex quantity, so I have both magnitude and phase on it as well. Okay. Now I mentioned that we were doing some laser work tonight, right? And so what does this have to do with a laser? Well, you may know, or you may not, that a laser is, I'm being old-fashioned here and drawing a gas laser, but a laser is a gain element for light, nestled nicely between two mirrors. Okay? And mirrors come as a finite aperture, right? And so the light that comes out of this gain spills over on this aperture. Only the ones that hit the aperture get reflected back. The stuff that spills over the edge is lost. This new reflection goes back, and again gets spatially filtered. So if I unfold the two mirrors, if I unfold this cavity, I'm left with a series of finite open apertures. Okay? So the aperture problem that I showed you is a representation, an iterative representation of what's going on with the light as it bounces back and forth between these two mirrors. So those two mirrors of the laser cavity act as a spatial filter for the light, and that's the essence. That's one way of developing what's called a mode for that laser. Okay. Now, one of the things that you probably thought of when I was describing this, and I was describing the spillover, the light that's lost. Go back to the aperture. The light that's blocked, all the light that winds up over here and is blocked by that aperture, that's lost. That light goes away. And so if I go through 100, 200 round trips, 100, 200 of these apertures, I'm throwing away a lot of my light. Okay? But in a laser, that's okay, because I've got this gain element inside of it that refreshes or boosts up the light level again. Okay, as long as I shove energy into that laser rod or that gas tube, then I have potentially a feedback mechanism with gain. And so from that perspective, this is an amplifier with a feedback loop. Okay, so I have a nice little oscillator. That's another model of a laser for the amount of power that comes out. So the spatial filtering. So the way I'm presenting this is the spatial filtering acts to shape the beam of light, and the gain element that we won't worry too much about acts to refresh whatever's lost by that low pass spatial filtering that goes on. Okay, and that's sort of a picture of how this happens. So if we take a look at this, there's also some little odds and ends that I won't worry. We have to worry a little bit about some geometric factors for the phase, how the phase comes together, and that's what this guy is doing. This, as I said before, is a spherical wavefront. This is the distribution of the electric field, or the field distribution, the amplitude and phase that falls on the aperture. Just some constants out in front that, again, we won't really worry too much. And so the idea is that we iterate from field to field, aperture to aperture. We see how the field, this U of P as a function of the size of the aperture, how that progresses as the mode is established. And one of the nice things about this is we can start with a any old integral, any old distribution, we successively spatial filter, and then a steady state distribution is actually established, and that we call a mode, okay, of this laser. And we can solve for that mode in a variety of ways, but this particular work is really clever, really sweet, because it for the first time it shows you where a mode comes from, right? I mean, I think many of you may have in other courses or even in this one have calculated modes of waveguides, for example, in homework and so on. But that's the steady state answer. This is actually better because this is like, where does it come from? And really what we're going to find, is after a few hundred of these iterations, UP will equal UP minus 1. And when that happens, that will be the establishment of the mode. Okay? And what I'll show you is that that's going to happen irrespective of what I guess my starting U of P equals 0 is. And that's a really interesting philosophical result. Okay, this work was done by Fox&Li by a researcher by Dr. Fox and Dr. Li at Bell Labs in the 1960s, right at the dawn of the laser. Right when the laser was first invented, there was a lot of questions about what it was, how it worked, and this is one of my favorite early papers that really talks about how this works. And it's a silly numerical, calculation, but you also have to remember that computers were fairly rare in the 60s, and so having this kind of computing power was only really available at a place like Bell Labs or a few other places. So again, it was a remarkable numerical work at the time. Now you can blow it away on your cell phone probably. Now, so what this is this is a plot of the magnitude, and what I've done is I've gone off to, if this is my aperture, I've gone to some point, say like there, or maybe closer to the center, and I've just said, what is the amplitude as a function of the number of iterations? So in other words, what's the magnitude? Remember, it's complex quantity, so I take the real part squared, the imaginary part squared, and I square root it, and I say, what's going on there at each iteration? And you see, I start at 0, I go to 50, 150, and so on, and I'm doing this stupid integral. I'm doing again and again and again. Okay, and you'll see if this is kind of interesting. It's all over the map, and then it settles in to a steady value, and you can figure out exactly where you want this to be. But it looks to me like it's a steady value somewhere around 200, 250 iterations. So after 200 or 250 iterations, I'm making the same measurement at that point. I'm observing the same field, and in fact, if I go to any of these points in here, I'll have different trajectories, but they'll all flatten out after a couple hundred, 250 round trips. And just to put this in perspective, right? If I have a cavity that's about a foot long, and that's about typical of what these early lasers were. About a helium neon laser was about a gas cell, about a foot, maybe a little longer. Mirrors there. So the single pass from aperture to aperture was a nanosecond, right? And so after about 200 nanoseconds, or for the first 200 nanoseconds, you had all this kind of oscillations, but then the mode kicked in and was steady state. So as you fired on the laser, as it evolved, as it settled itself into that steady state in really very, very short of transient time. Okay, and so that's what the significance of this round trip, and that's what the significance of the behavior of this particular damped oscillation looks like. Okay, and so There it is at a slightly different, for a slightly different set of A over B, slightly different parameters. So the geometry of this laser influences, as you would expect. The more spatial filtering happens, the faster the settling time. If the apertures are really big and close together, there's not a lot of spatial filtering going on, not a lot of diffraction. It takes longer for the mode to be established. Okay? And here's what the mode looks like. Here's what the modes look like for this particular case. It's a little clipped off, but you can see a nice sort of a peaked distribution that looks like that, and you can see the remnants. That's the first interpretation of that. You can see the remnants of the diffraction. You see these little ripples here? Those are spatial frequencies that haven't quite been filtered out, that are supported, in fact, by this. So the general distribution is a nice peaked distribution, and then there's some perturbations on top of it that are from the diffraction piece of it. Now, if you solve, and in fact you have to look at the cavity kind of carefully, and it's a derivation that I was debating doing. It takes about 2 to 3 lectures to do. But if you solve this, this is so annoying. Why do you think that does that?
You need to be done.
I've done that a million times. What do I do?
Clicking back to side.
It's part of the program. That's the problem. I don't know.
If that's up, you probably can't scroll.
What's the flashing windows?
That's for security, but I don't want to.
Is it trying to do something?
This okay.
There it is.
The check spelling is part of the Adobe Acrobat, I think, or the probably Microsoft Explorer or something like that. Okay, and remember I said it was phase, and here's the phase front, and really what the phase front is remember the phase. I think of the phase front as sort of the lens that the beam carries around with it. Okay. I remember where I was going with it. I'm sorry, I got distracted by this check spelling thing. If you solve the mode from the Maxwell's equations into the wave equation, you have to make one little assumption that I'll talk about later on. But if you solve that, what the kind of mode that you actually end up solving for is called a Gaussian mode, a Gaussian beam, and really that's another name for the bell shape, the bell curve. Okay, and if you remember your central limit theorem from probability and statistics or random processes, a successive number of low-pass filters gives you a distribution that's the normal curve or the bell-shaped curve or in this case the Gaussian mode. Okay, so you get in this case you get approximately the Gaussian mode from the buildup of the spatial filtering from the application of Huygen's integral again and again and again, and if you solve for the steady state distribution from Maxwell's equations, you would get the mode in a different way. Again, the difference that I like about this is that you're watching the mode build up. You're not making any a priori assumptions that it's going to be Gaussian. You're not guessing a Gaussian. You're smearing any old light distribution. You're watching the physics evolve numerically. It's a really nice thing. So magnitude and phase, and remember the phase front will determine where the magnitude goes. It's a little bit like the Kramers-Kronig relations, a little bit like the Hilbert transform of the real part and the imaginary part. Not quite the same, but pretty close for these things. Okay, let's see. Again, this is just iterations and settling times. I think this is for the same cavity, but for slightly different dimensions. And here's the different modes, again, for different dimensions. And if I plot this Fox&Li number, and what I mean by that is the settling time, how long it takes to settle, and I plot as a function of the size of the cavity, I see basically a trend that, the more spatial filtering I have, the faster my mode converges. Okay, so that's just something we sort of talked about, and this is a little bit more definitive. Okay, now I went and I revisited this problem years and years later after Fox&Li, and I decided that I would actually change what was going on inside between the two mirrors, and I wanted to do a much more physical model. So I remembered that I was doing a laser, and I did gain. I did the gain distribution, and so you'll see that I picked a gain distribution that, depending on my current or depending on a control parameter, okay, the amount of energy that I was putting into the laser, for low currents, it peaked in the center and went to 0 at the end. That's a very, very, very generic and reasonable gain distribution. If you're talking about a gas laser and you're shoving current down the axis of the gas laser, it's a fluid flow, and it's going to be, and you're going to get lower current on the edges than you will in the center. So you'll have a higher gain in the center than you will on the edges. If you're injecting current into a semiconductor, again, you'll have more gain in the center than you will spilling over away from the edges. So you'll be peaked. If you're pumping a YAG rod, a solid-state laser with a diode laser, you're probably end pumping it. And again, the distribution of light from the diode laser will be peaked. It'll be end pumped, and again, it'll be distributed in the center. Okay. If, however, you overdo it, you crank up your current in your gas laser, you'll hit some kind of a saturation, and then some interesting things happen. You'll actually see not a peak in the center, but actually peaks on the wings. Okay? And what I want you to think about this, and this is, you don't have to be a laser expert to sort of think about this. Light goes where the gain is. The gain gives you the light. So if I have more gain here, I'm going to have higher gain. I'm going to have higher light here. If I have more gain out here, well, I'm going to have more light out here. Okay? So the movement of the current from a distribution that looks like that to a distribution that looks like that means that my light distribution is going to move from the center to the wings. Okay? And so I want to model that, I want to look at that, I want to interpret that in the context of this Fox&Li picture. So I want to see what kind of modes come up with all these different gain distributions. Okay? And here's, if you're interested, is the function, Bessel functions. It's Bessel functions because it's actually solving for the current in a cylindrical pipe, and the solutions naturally of the wave equation for that current flow naturally leads to Bessel functions, and this is the fit of the Bessel functions. So this guy gives you the initial peak, and this guy takes it away. Okay, not too terribly important for the details of it, but it is founded in some tractable theory. And if I increase the current, and notice this is for very small currents, so a 1/4 milliamp to 2.5 milliamps to 25 milliamps. Just remind you what those look like on the current distribution. They're all curved like that. Okay, so they're all either flat or well-behaved curves that look like that. I wish I knew one. I know there's a way of doing it. I wish I knew one way of erasing the whole screen. I'll just drive you crazy. Just you watch me erase bit by bit by bit. And so this is what it looks like. And you see that as before, you had these diffraction peaks for mostly flat current distributions. By the time you get up to 25, you've got a really nice quadratic. And look how smooth and nice that beam is. And that's starting to look very, very much like a Gaussian. Now, do you remember when I said solving the wave equation for the mode? And I said that there was some little detail that you had to do? Well, in order to really get a Gaussian out of that wave equation, what you had to do is you had to assume a distribution of gain or a distribution of index that was peaked in the center and rolled off quadratically. Okay? So you had to solve a differential equation that had non-constant coefficients, and the non-constant coefficients was a quadratic dependence, and it didn't care whether it was the real part of k or the imaginary part of k, whether it was the gain or whether it was the index of refraction. Index of refraction focuses, bends the light towards the center of the higher towards the higher index, and the gain creates the light where it's peaked. Okay, and so as the current distribution looks more and more quadratic, the mode smooths out and becomes more and more like a Gaussian. Okay, so that was really nice because that was the missing link between Fox&Li and the Gaussian mode. In fact, if you model the Fox&Li for the right case, out pops the Gaussian mode that you would calculate from the analytics. Okay, and again, you're doing this in a way that's not assuming a Gaussian. It's just being filtered, really, again through the central limit theorem. I think into its nice path. Also, remember one very interesting thing about the Gaussian from your signals and systems, or I bet you may have forgotten this. But do you remember what the Fourier transform of a Gaussian is?
Gaussian.
It's a Gaussian. So remember the lens from last time? The aperture, the slit? The lens, I called it a Fourier transform lens because we went from a rectangle pulse to a sinc function. Well, if a Gaussian, the Fourier transform of a Gaussian is a Gaussian, if I take a Gaussian beam and I put it through a lens, it's still a Gaussian. Except if it's a big beam, then and I go through a lens that becomes a sharp beam, and so on and so forth. So these laser beams, the fact that they're Gaussian is really nice when it comes to propagating them through optical systems and so on, because of this Fourier transform property of a Gaussian Fourier transform of a Gaussian is a Gaussian. So this is kind of an interesting thing because we're seeing the central limit theorem, we're seeing the solution to the wave equation, and we're seeing this Fox&Li approach, all kind of showing what's all converging on a very, very magic bell-shaped distribution. Okay, so kind of mystical if you think about it. And so this is the phase, and the other piece of the Gaussian mode, if you solve Maxwell's equations and put in the quadratic index or the quadratic gain. Remember, it's an electric field, so it has a real part and an imaginary part. What that means, it has an amplitude distribution, and it has a phase distribution. Well, the phase distribution for a Gaussian beam is a spherical wave. It is a curved spherical wave front, and this is plotted the phase, and there's our nice curved spherical wave front when you get a nice quadratic gain distribution. Okay? So all is well in the world for now. Okay? Let's see. Oh, okay. This is keep increasing the current. And remember, when you increase the current, it flattens out on top, and then it becomes then it turns over, and it actually dips a little bit in the center. And just to remind you where that happens, flip back to this. You see that when you're around 50, you're pretty flat, right? When you're 50, when you're up at 100, you see a fairly appreciable well in the center. So you start to be peaked on the edge. You go from flat to peaked on the edge between 50 and 100 milliamps of this argon laser that I happened to be looking at modeling at the time. Okay, and let's see. So now I moved from my 25 to my 50, and then and you start to see the diffraction ripples again. So I'm returning back to my baseline of being of more no real current, no real gain, and it should alert you that I've been plotting things in terms of 25, 50, 100, 125, 150, and now all of a sudden I'm giving you a result that's 82 milliamps, and you should sort of think, why is he doing 82 and not 75 or not 100? What? So that should cross your mind. I'm stopping at an odd place. Okay. Maybe I'll tell you why. But you should think about it. You should just be alert. You should be alert to that. You won't be able to figure it out. If I look at my phase fronts, remember the nice, smooth, curved phase front, the spherical wave front for the spherical gain distribution. It's a nice curved gain distribution. As it flattens out, it becomes a little bit. And then notice, look what happens here. At 82, the phase fronts break into two, a curved here and a curved here. Okay, so I have sort of a peaked distribution. And notice, let's see if I can show this. If I draw a line across from there to there, the curves actually just tiptoe over that line. Zero phase, so I actually have a phase reversal. I actually have just the beginning at this weird 82 number. I have just the beginning, just the beginning of this weird phase reversal that's getting ahead of itself, and that can be a problem. Okay. As you know, as you may have, if you've taken particularly, say, an RF microwave amplifier class, you know that that really what gets you unstable is your phase response, right? And the same thing is going to happen in this case as well. So, if I look at my mode width, the phrase, this is kind of weird. This is 1 milliamp, and then this is 100. This is 10 milliamps, and this is 100 milliamps. You can see that as the gain sharpens, I have a nice decrease in my mode distribution, and then as I get higher, I get an increase back up again in my mode distribution. This dotted line here is just an analytic expression that I calculated, and it fits reasonably well. Not perfectly, but reasonably well. Okay, at least the trend is there. And here's my settling time. And this is for, let's see. This is for 25 milliamps, so it's fairly nice and peaked. And the settling time is really fast. Okay? So the mode wants to happen when there's that nice gain peak, just like Maxwell's equations solution wants it to happen. And if I go up to 82, it happens again fairly steadily. And then again for a slightly higher, it takes a little bit longer. So at 82 milliamps, it's taking longer to settle into a steady state. The Fox&Li number is going back up, and that's what this is plotting here. This is the mode settling time, the Fox&Li number. It goes way down. That's 1. That's 10. That's 100 milliamps. The weird 82 is floating around right in here, and well-behaved modes settle really fast, and then notice what happens here. Woomph. Through the roof. Okay? Very, very fast unsettling. It still settles, but it takes a while. Okay? This is the gain. So we haven't talked a lot about it, but as you lose light, in the numerical algorithm, you put light back in, you amplify back up, and this is what this gamma is. It's the arbitrary constant that you do so that you have the same amount of power, aperture by aperture by aperture. And it's a measure, in fact, of how much spatial filtering is going on. The more gain you put in there, the more of this gamma you put in there, the more light you've lost because of the spatial filtering. Okay? So that's calculated and reported there. And here it is again, the gamma for the different gain distributions. Okay. Now, if I go up, remember I stopped at 82, right? And for higher currents, 142, 175. 225. Remember that was quite peaked on, it was quite donut-shaped, annular-shaped gain. And so the light goes where the amplitude is. And so I've got a nice ring or a nice donut mode of my laser beam. Okay? And again, there's an anomaly, there's a weird thing going on with I'm not giving you 100, I'm not giving you 125, I'm giving you 82, nothing, and then 142 again. Okay? And then I'm able to go back up by, nice round, evenly sensible numbers of gain. Okay? So something weird is going on between 82 and 142 right when the peak in the center is fighting the two peaks on the edges of the gain. There's the phase distribution. There's the phase front distribution. And again, if I look at this, I have a beam out here with a nice curved wavefront and a beam out there with a nice curved wavefront. Those are focusing fronts. But look at what's happening in the center. In the center, the curvature is the other way, and so that's a defocusing lens. So if you think about a phase front as the lens that the beam carries around with it, I have focusing, and I have a defocusing here. Okay? Phase front. Now, to refresh my memory exactly where this is what happens for the calculations of 100 milliamps. That's right in the middle between this 82 and this 142 milliamps, right? And take a look at what happens here. These are, let's see, I want to remember exactly what I've plotted here. This solid line here is the average field distribution, the magnitude of the average field distribution. And it looks fairly okay. Right? Little ripples on it, fairly well behaved. But if I look at what's going on between, not on the average, but at each and every case, I get wildly different field distributions. I have one that looks annular. I have another that's sharply peaked. And then I have another one. Oops, sorry about that. I have another one, and when we were doing this Batman was a movie that had just come out, and my graduate student looked at that and said it looks like the caped, the Batman kind of a caped crusader kind of a mode. And what we noticed was, and this was actually kind of interesting. We had no idea nothing was converging. And so what we did was we went to a typical voltage, a typical current like this, and we printed out the waveforms. And what we identified was 21 distinct waveforms. They basically fell into these three categories: the Batman, the tightly peaked, and the winged one, the annulus one. And what we did was we had 21 of these, right? We had 7 of these that looked like Batman, 7 of these that looked tightly focused, and 7 of these that were annulus. And we printed them out and we laid them out in the hallway, and we sorted them. And what we would find was, and this makes sense, this guy here collapses in on itself to sharply peaked. The sharply peaked diffracted into the Batman, which moved back into the annulus. So there was this periodic cycling of distributions, of mode distributions, that you would miss if you were just solving for the mode of the cavity. You would miss if you were looking at the average power out of the laser, because remember, this is cycling through at gigahertz. These mode structures were cycling through at gigahertz. And in fact, I think we were kind of modeling a semiconductor laser, because that was the interest at the time. And so it was actually going at hundreds of gigahertz, or terahertz even, of the cycling. So very, very interesting dynamics of the modes. And I also bring that up because it was a puzzle. So much of research today, you sort of think you know the answer, and you just spend all this time, getting the math right and making, confirming your hypothesis or your theory. This was really fun because we had no idea what was going on, and it wasn't until we printed everything out and went out in the hallway and visually sorted did we construct the story of what was going on. So it's a rare instance of you wake up in the morning, you have no idea what's going on, and you go, aha. That's what, and then afterwards it all makes perfect sense. So that's sort of a advertisement for research. You should look for unexpected things and enjoy some of the interesting quirks that nature gives us through science and engineering. But anyway, that was what was going on there. And once we did that, everything kind of came together. So here's this gamma again. Here's this gamma. The asterisks were stable solutions, a single mode distribution being generated. And you'll notice that those occur up to 82 and after 142. So the instability or the unstable region happened between those two cutoff points of 82 and 142. That's why I clipped my results. Stopped my results at 82 and picked it up again at 142, because I had this hash, this garbage, if you will, going on between the two. And so we went back in and we averaged. Remember, we averaged 21 in that case, but not always 21. We went in and we averaged the mode to fill in the gap between the two. And if you average it, it has some discontinuities, but it looks pretty darn smooth from a curve. So on average, everything's working pretty nicely, but there's very, very strange dynamics going on in there. And laser instabilities and instabilities of these things is a very rich science. Nonlinear dynamics. Maybe some of you know chaos theory, and to me, this hints at a lot of that. A new type of instability in a system that is very, laser systems can be in fact chaotic, and I mean that in the very technical sense of the term. You can have instabilities that are not chaotic. You can have things that look noisy and don't pass the test for chaos. Then we also did some other imperfections such as a tilt on the gain, or rather a tilt on the thing, and we saw that sure enough the light goes there. Our thought here was to build some sort of a modulator or some sort of a beam steerer based on this instability, and that's still actually a pretty good thing to be. I think probably dusting that off and trying to do that would actually be useful and be much more possible now than it was with the crude diode lasers that we were working on years ago. And again, mode settling time. There's another just imperfections here. Skip through some of this. We took the same theory. Then we took the same theory and we applied it into a completely different geometry. Okay, there is a very famous mode that exists. Has anyone been to London, England? I'm sure there's a London, Texas, but in London there's a St. Paul's Cathedral that you might have seen pictures of. It was built right after the Fire of London by Wren, and it has a beautiful dome. It's one of the early dome examples of a dome, it survived the Blitzkrieg in World War II, so it's kind of famous on that. And then the other very famous thing, and if you visit, you need to do this as good students of Fields and Waves. Go up to the gallery inside the dome, and the gallery is called the Whispering Gallery. Okay, and so if you sit on the bench of the Whispering Gallery, and you take a friend, and the friend sits here, and you sit here, and you turn and you don't look at your friend, but you whisper. The sound will be guided in a very, very low loss mode all the way around the perimeter of the gallery, and your friend can hear it better in this ear than in this ear. If you then get really mad at your friend and tell him to go sit on the other side of the gallery, and you repeat the experiment, you can have a wonderful conversation by whispering and have him hear it, and then whispering and him guiding there. If you tried to shout across the dome, it wouldn't work at all. But if you whisper and you use this very high quality factor resonance of this thing, and it's a wave phenomenon. It's an acoustic wave, but it also happens with light and so on. And so there has been at least 20 years of really interesting research in sensors and in making very, very high Q resonators by taking spherical structures. And in fact, a friend of mine, Kerry Valhalla at Caltech, holds the record for the highest quality factor resonator based on this Whispering Gallery Road resonance in a silicon, making a silicon waveguide, where he then very carefully etches the sides so that it's not just straight, but it's curved, and guides it beautifully in both the theta direction and this azimuthal direction. Just a really, really nice piece of micro machining work that pays off with the world's highest quality factor filter. You may ask, why do you care about that? Well, that is the ultimate precision measure. If you ask, how good is your watch? I lose 3 seconds a day. That's a statement, number of seconds per day, number of seconds in the day. That's a statement of the quality factor of your watch, okay, of the oscillator of your watch. And so I think he's achieved 10 to the 15th quality factors in these devices. I have another friend at SMU who makes these spherical resonators out of PDMS. Does anyone know what PDMS is? Does anyone have an idea? Has anyone played with it? It's very soft rubber. It has the consistency of just like rubber cement. If I wasn't being recorded, I would say that it had this consistency of snot, but that's what we. So it's that kind of spongy stuff, and you can get them very transparent, around 1.5 microns, and you launch the waveguide. And now think about this. This is a soft rubber ball, right? And so any kind of breathing on it, or any kind of a pressure wave, or anything is going to distort that sphere into a spheroid, into like a football shape, and it's going to move the resonances around. And so if you have very, very sharp resonances, in this case about 10 to the 11th or 10 to the 12th, you can make a very, very precise measurement of that shifting of that waveguide mode, which is also related to the pressure. And so you have one of the most sensitive pressure meters. Or if you dope it, you can measure electric fields. And we hold the record for the most sensitive electric field measurement. It's about a volt per meter, a couple volts per meter. And if you think about what that is, take a 9-volt battery and attach wires to both of the terminals and hold those wires a yard apart. And that's a volt per meter, right? So you get very, very small, very, very small, or what, three yards apart, right? So it's very, very small fields. And yet we can, with this kind of technology, we can sense it. So the question is, how fast are these? And the question is, how does the mode build up? And this has been looked at by Rayleigh, obviously. Looked at by Meade by Lorentz theory. Looked at the steady state solution of Maxwell's equations, or the wave equation, leads these funky spherical harmonic special functions. And so the problem is really, really well known. Lots of applications for it. And, of course, low threshold lasers. And nonlinear processes as well in these materials. And so what we did was we said, okay, well, let's look at it from the Huygens principle. And how much time am I burning up here? It's okay, I've got time. So what we did was we created a circle, a sphere, right? And we lined our sources, our spherical wavefront sources, over some part of the sphere. Okay. Now what we were doing with this is we were coupling light into it. So the typical setup is you get a little an inkjet printer or something like that, and you create these balls of fluids there, and you pump them with a high power laser, and you catch a little bit of it, and then the mode scatters and fills around the whispering into the whispering gallery mode. And so what we did here was we said, okay, here's the incoming laser beam, and it's going to propagate around the circle, around the sphere, around the edge of the sphere. And so what we did was, remember we had apertures. Well, this was a sliding aperture. So the way we set this problem up, and it's kind of creative and not perfectly correct, but again, that's part of science and understanding nature. So we had a sliding aperture that we walked around the whole sphere. Okay, so we loaded it and we watched it propagate around the sphere. The spatial filtering was done by the propagation of the Huygens integral. And do you remember we had the different reflection coefficients for the different polarizations for TE versus TM? Do you remember the plane waves at an oblique angle on a dielectric? And here they are. Here's the reflection coefficients for the S polarized light and the P polarized light. Okay, and so notice that it depended on the angle, and notice then that as we walked around, that angle changed, so the reflection coefficient changed as well. Turns out we didn't have to do that, but it was the right thing to do, and it was easy to do. It wasn't terribly difficult to do. So, and here's our the other thing that was weird about this was what's the circumference of a circle? What was it? 2 pi r. Okay? Why do I mention that? Well, pi is an irrational number, right? And so you can't subdivide the sphere into equal parcels because of that pi. Okay? Because you can't, you have this infinite number of digits. And so what we had to do was we had to pick our sampling very carefully relative to pi. So we had integer numbers of pi, a different kind of aliasing, kind of a problem. And so what would happen is if we didn't line this thing up perfectly, the mode that we evolved in these would slide around. Do you know like you take a strobe light on a timing belt in a car, or you photograph a movie, an old movie, photographing a tire, a car chase, and sometimes the wheels look like they're going backwards. It was that kind of an aliasing problem, except applied to this numerical technique. But what we did was we got all that stuff worked out, and we figured out what was going on. And here's our mode distributions as a function of the angle around the perimeter. So here pi is here. So as we walked around, we got this mode distribution, and eventually there's the after some more iterations, it kind of goes into that, and then finally it settles in on these very, very sharp resonances. So as you walk around the drop, you'll see bright light, dark, bright light, dark, bright light, dark, a zebra stripe, if you will. And so this mode evolution did settle into exactly these kinds of modes that you expect, and you can calculate from all the other theories that you do. So you observe this experimentally, and you also observe this. Here's our mode settling time. So you can see, in fact, it's settling in, and it settles in after a certain amount of round trip time. Again, another settling time plot, and here's some experimental comparisons. So these are, here's your high low light, your zebra stripe as you go around the circumference of the die. So this is agreement between theory and this new theory and this experiment. And some of you may remember Professor Cantrell, who passed away just a couple years ago. Here's his calculations based on me theory and with all the spherical harmonics. And again, his steady state theory nicely shows the zebra striped high low resonances, exactly like the Huygens principle does as well. So all this is all this tends to kind of come together. So this Huygens principle, this convolution, this Green's function approach, the spherical wave approach, is wildly versatile, very, very, very flexible. And so we've looked at it. Here's an optics problem, but it's not, because this can also be scaled to any RF, and you can use. We've used it to model regular antennas, horn antennas, apertures, diffraction gratings in optics, laser beams, and resonators of very, very high quality factors. So it's really a very, very versatile thing. What I was arguing here for the sphere was the me theory that Cantrell uses works brilliantly as long as you have a sphere. Okay? But you never will have a sphere. So think about this inkjet printer that's creating these droplets. These droplets actually are going to wiggle and oscillate through space. They're going to be more like a football shaped than they are going to be like a sphere. And you can't. And so when you model it with me theory, the spherical harmonics, you run out of symmetry. you don't have the right answer. So, but this mode evolution, this Huygens approach, doesn't care. It doesn't care that I have a sphere or I have a stadium-like structure and stuff. So I wanted to write the paper, Waves in a Stadium-like Medium, Stadium-like Structure. This was back in the time when, football, audiences would get up and stand up the waves. So kind of a pun, but from another decade. So forgive that. I wanted to pick this lecture to close on for a number of reasons. One is it ties, I think, really nicely into the spherical waves that we were talking about for the last couple of weeks. The convolution integrals we've been talking about since we began our antenna problem. I also wanted to get a little bit of the flavor of research, and for some of you, because I know that some of you are doing research, and I hope all of you will have we'll do a little bit of it at least before you graduate. And really, one of the fun things about that is, we talk about papers and posters and presentations and results and all this and funding and everything, but really the fun of it is in the discovery, and it is looking at nature in a completely new way. And both of these problems amused me greatly from that scale, from that perspective. The ability to look at these modes in St. Paul's Cathedral, and in fact, I went back there last year with my two collaborators on the rubber ball problem, and we did the experiments in macro scale that we'd been doing on the optical table in micro scale. It was really a lot of fun. But when you think that, I'm thinking in terms of this. I'm thinking in terms of the Mie theory, spherical harmonics. I'm thinking in terms of the Airy functions that actually form the shape of the mode, that as it skitters around the outside. And I'm thinking about the propagation of these spherical wavefronts as they bounce off the walls of that cathedral. And so again, looking at the world in a quantitative way, in a different way, in a physical way, is really we forget that's a rich part of our study. We're so, as engineers, we're so caught up sometimes with the rational and the relevant and the tech transfer and all that. Sometimes we can do all that, right? But we can also enjoy, what mathematics and physics and nature provide for us as well. Okay.